Parallel computing is a type of computation in which many calculations are carried out simultaneously, operating on the principle that large problems can often be divided into smaller ones, which are then solved at the same time. There are several different forms of parallel computing: bit level, instruction level, data and task parallelism. Parallelism has been employed for many years, mainly in high-performance computing, but interest in it has grown lately due to the physical constraints preventing frequency scaling, as power consumption by computers has become a concern in recent years. Parallel computing has become the dominant paradigm in computer architecture, mainly in the form of multi-core processors. Parallel computing is closely related to concurrent computing. They are frequently used together, and often conflated, though the two are distinct. It is possible to have parallelism without concurrency, and concurrency without parallelism. In parallel computing, a computational task is typically broken down in several, often many, very similar subtasks that can be processed independently and whose results are combined afterwards, upon completion. In contrast, in concurrent computing, the various processes often do not address related tasks. When they do, as is typical in distributed computing, the separate tasks may have a varied nature and often require some inter-process communication during execution. Parallel computers can be roughly classified according to the level at which the hardware supports parallelism, with multi-core and multi-processor computers having multiple processing elements within a single machine, while clusters, MPPs, and grids use multiple computers to work on the same task. Specialized parallel computer architectures are sometimes used alongside traditional processes for accelerating specific tasks. In some cases parallelism is transparent to the programmer, such as in bit-level or instruction-level parallelism, but explicitly parallel algorithms, particularly those that use concurrency, are more difficult to write than sequential ones, because concurrency introduces several new classes of potential software bugs, of which race conditions are the most common. Communication and synchronization between the different subtasks are typically some of the greatest obstacles to getting good parallel program performance. A theoretical upper bound on the speed-up of a single program as a result of parallelization is given by Amdahl's law. Background: traditionally, computer software has been written for serial computation. To solve a problem, an algorithm is constructed and implemented as a serial stream of instructions. These instructions are executed on a central processing unit on one computer. Only one instruction may execute at a time. After that instruction is finished, the next one is executed. Parallel computing, on the other hand, uses multiple processing elements simultaneously to solve a problem. This is accomplished by breaking the problem into independent parts so that each processing element can execute its part of the algorithm simultaneously with the others. The processing elements can be diverse and include resources such as a single computer with multiple processors, several networked computers, specialized hardware, or any combination of the above. Frequency scaling was the dominant reason for improvements in computer performance from the mid-1980s until 2004. The runtime of a program is equal to the number of instructions multiplied by the average time per instruction. Maintaining everything else constant, increasing the clock frequency decreases the average time it takes to execute an instruction. An increase in frequency thus decreases runtime for all compute-bound programs. However, power consumption P by a chip is given by the equation P equals C times V2 times F, where C is the capacitance being switched per clock cycle, V is voltage, and F is the processor frequency. Increases in frequency increase the amount of power used in a processor. Increasing processor power consumption led ultimately to Intel's May 8, 2004 cancellation of its Texas and Jayhawk processors. which is generally cited as the end of frequency scaling as the dominant computer architecture paradigm. Moore's law is the empirical observation that the number of transistors in a microprocessor doubles every 18 to 24 months. Despite power consumption issues, and repeated predictions of its end, Moore's law is still in effect. With the end of frequency scaling, these additional transistors can be used to add extra hardware for parallel computing. Amdahl's law and Gustafson's law optimally. The speedup from parallelization would be linear. Doubling the number of processing elements should halve the runtime, and doubling it a second time should again halve the runtime. However, very few parallel algorithms achieve optimal speedup. Most of them have a near-linear speedup for small numbers of processing elements, which flattens out into a constant value for large numbers of processing elements. The potential speedup of an algorithm on a parallel computing platform is given by Amdahl's law, where latency is the potential speedup in latency of the execution of the whole task. S is the speedup in latency of the execution of the parallelizable part of the task. P is the percentage of the execution time of the whole task concerning the parallelizable part of the task before parallelization. Since latency less than 1, it shows that a small part of the program which cannot be parallelized will limit the overall speedup available from parallelization. A program solving a large mathematical or engineering problem will typically consist of several parallelizable parts and several non-parallelizable parts. If the non-parallelizable part of a program accounts for 10% of the runtime, we can get no more than a 10 times speedup, regardless of how many processes are added. This puts an upper limit on the usefulness of adding more parallel execution units. When a task cannot be partitioned because of sequential constraints, the application of more effort has no effect on the schedule. In practice, as more computing resources become available, they tend to get used on larger problems, and the time spent in the parallelizable part often grows much faster than the inherently serial work. In this case, Gustafson's law gives a less pessimistic and more realistic assessment of parallel performance. Both Amdahl's law and Gustafson's law assume that the running time of the serial part of the program is independent of the number of processors. Amdahl's law assumes that the entire problem is of fixed size so that the total amount of work to be done in parallel is also independent of the number of processors. Whereas Gustafson's law assumes that the total amount of work to be done in parallel varies linearly with the number of processors. Dependencies. Understanding data dependencies is fundamental in implementing parallel algorithms. No program can run more quickly than the longest chain of dependent calculations, since calculations that depend upon prior calculations in the chain must be executed in order. However, most algorithms do not consist of just a long chain of dependent calculations. There are usually opportunities to execute independent calculations in parallel. Let pi and pj be two program segments. Bernstein's conditions describe when the two are independent and can be executed in parallel. For pi, let E be all of the input variables and OI the output variables, and likewise for pj. Pi and pj are independent if they satisfy violation of the first condition introduces a flow dependency, corresponding to the first segment, producing a result used by the second segment. The second condition represents an anti-dependency, when the second segment produces a variable needed by the first segment. The third and final condition represents an output dependency. When two segments write to the same location, the result comes from the logically last executed segment. Consider the following functions, which demonstrate several kinds of dependencies. 1. Function dep2. C equals b3. D equals 3 c4. End function. In this example, instruction 3 cannot be executed before instruction 2, because instruction 3 uses a result from instruction 2. It violates condition 1, and thus introduces a flow dependency. 1. Function no dep2. C equals a asterisk B3. D equals 3 asterisk B4. E equals a plus B5. End function. In this example, there are no dependencies between the instructions, so they can all be run in parallel. Bernstein's conditions do not allow memory to be shared between different processes. For that, some means of enforcing and ordering between accessors is necessary, such as semaphores, barriers, or some other synchronization method. Race conditions, mutual exclusion, synchronization, and parallel slowdown subtasks in a parallel program are often called threads. Some parallel computer architectures use smaller, lightweight versions of threads known as fibers, while others use bigger versions known as processes. However, threads is generally accepted as a generic term for subtasks. Threads will often need to update some variable that is shared between them. The instructions between the two programs may be interleaved in any order. For example, consider the following program. If instruction 1b is executed between 1a and 3a, or if instruction 1a is executed between 1b and 3b, the program will produce incorrect data. This is known as a race condition. The programmer must use a lock to provide mutual exclusion. A lock is a programming language construct that allows one thread to take control of a variable and prevent other threads from reading or writing it. Until that variable is unlocked, the thread holding the lock is free to execute its critical section, and to unlock the data when it is finished. Therefore, to guarantee correct program execution, the above program can be rewritten to use locks. One thread will successfully lock variable v, while the other thread will be locked out, unable to proceed until v is unlocked again. This guarantees correct execution of the program. Locks, while necessary to ensure correct program execution, can greatly slow a program. Locking multiple variables using non-atomic locks introduces the possibility of program deadlock. An atomic lock locks multiple variables all at once. If it cannot lock all of them, it does not lock any of them. If two threads each need to lock the same two variables using non-atomic locks, it is possible that one thread will lock one of them and the second thread will lock the second variable. In such a case, neither thread can complete, and deadlock results. Many parallel programs require that their subtasks act in synchrony. This requires the use of a barrier. Barriers are typically implemented using a software lock. One class of algorithms, known as lock-free and wait-free algorithms, altogether avoids the use of locks and barriers. However, this approach is generally difficult to implement and requires correctly designed data structures. Not all parallelization results in speed up. Generally, as a task is split up into more and more threads, those threads spend an ever-increasing portion of their time communicating with each other. Eventually, the overhead from communication dominates the time spent solving the problem, and further parallelization increases rather than decreases the amount of time required to finish. This is known as parallel slowdown. Fine-grained, coarse-grained, and embarrassing parallelism applications are often classified according to how often their subtasks need to synchronize or communicate with each other. An application exhibits fine-grained parallelism if its subtasks must communicate many times per second. It exhibits coarse-grained parallelism if they do not communicate many times per second, and it exhibits embarrassing parallelism if they rarely or never have to communicate. Embarrassingly parallel applications are considered the easiest to parallelize. Consistency models. Parallel programming languages and parallel computers must have a consistency model. The consistency model defines rules for how operations on computer memory occur and how results are produced. One of the first consistency models was Leslie Lamport's sequential consistency model. Sequential consistency is the property of a parallel program that its parallel execution produces the same results as a sequential program. Specifically, A program is sequentially consistent if the results of any execution is the same as if the operations of all the processes were executed in some sequential order, and the operations of each individual processor appear in this sequence in the order specified by its program. Software transactional memory is a common type of consistency model. Software transactional memory borrows from database theory the concept of atomic transactions and applies them to memory accesses. Mathematically, these models can be represented in several ways. Petri nets, which were introduced in Carl Adam Petrie's 1962 doctoral thesis, were an early attempt to codify the rules of consistency models. Data flow theory later built upon these, and data flow architectures were created to physically implement the ideas of data flow theory. Beginning in the late 1970s, process calculi such as calculus of communicating systems and communicating sequential processes were developed to permit algebraic reasoning about systems composed of interacting components. More recent additions to the process calculus family, such as the pi calculus, have added the capability for reasoning about dynamic topologies. Logics such as Lamport's TLA+, and mathematical models such as traces and actor event diagrams, have also been developed to describe the behavior of concurrent systems. Flynns Taxonomy. Michael J. Flynn created one of the earliest classification systems for parallel computers and programs, now known as Flynns Taxonomy. Flynn classified programs and computers by whether they were operating using a single set or multiple sets of instructions, and whether or not those instructions were using a single set or multiple sets of data. The single instruction, single data classification is equivalent to an entirely sequential program. The single instruction, multiple data classification is analogous to doing the same operation repeatedly over a large data set. This is commonly done in signal processing applications. Multiple instruction single data is a rarely used classification. While computer architectures to deal with this were devised, few applications that fit this class materialized. Multiple instruction multiple data programs are by far the most common type of parallel programs. According to David A. Patterson and John L. Hennessy, some machines are hybrids of these categories, of course, but this classic model has survived because it is simple, easy to understand, and gives a good first approximation. It is also, perhaps because of its understandability, the most widely used scheme. Types of parallelism. Bit-level parallelism. From the advent of very large-scale integration computer chip fabrication technology in the 1970s until about 1986, speed up in computer architecture was driven by doubling computer word size, the amount of information the processor can manipulate per cycle. Increasing the word size reduces the number of instructions the processor must execute to perform an operation on variables whose size is greater than the length of the word. For example, where an 8-bit processor must add two 16-bit integers, the processor must first add the 8 lower-order bits from each integer using the standard addition instruction, then add the 8 higher-order bits using an add with carry instruction and the carry bit from the lower-order addition. Thus, an 8-bit processor requires 2 instructions to complete a single operation, where a 16-bit processor would be able to complete the operation with a single instruction. Historically, 4-bit microprocessors were replaced with 8-bit, then 16-bit, then 32-bit microprocessors. This trend generally came to an end with the introduction of 32-bit processors, which has been a standard in general-purpose computing for 2 decades. Not until recently, with the advent of x86-64 architectures, have 64-bit processors become commonplace. Instruction-level parallelism. A computer program is in essence a stream of instructions executed by a processor. Without instruction-level parallelism, a processor can only issue less than one instruction per clock cycle. These processes are known as subscalar processors. These instructions can be reordered and combined into groups which are then executed in parallel without changing the result of the program. This is known as instruction-level parallelism. Advances in instruction-level parallelism dominated computer architecture from the mid-1980s until the mid-1990s. All modern processes have multi-stage instruction pipelines. Each stage in the pipeline corresponds to a different action the processor performs on that instruction in that stage. A processor with an n-stage pipeline can have up to n different instructions at different stages of completion and thus can issue one instruction per clock cycle. These processes are known as scalar processors. The canonical example of a pipelined processor is a RISC processor, with 5 stages: instruction fetch, instruction decode, execute, memory access, and register write-back. The Pentium IV processor had a 35-stage pipeline. Most modern processors also have multiple execution units. They usually combine this feature with pipelining and thus can issue more than one instruction per clock cycle. These processes are known as superscalar processors. Instructions can be grouped together only if there is no data dependency between them. Scoreboarding and the Thomas-Illo algorithm are two of the most common techniques for implementing out-of-order execution and instruction-level parallelism. Task parallelism. Task parallelisms is the characteristic of a parallel program that entirely different calculations can be performed on either the same or different sets of data. This contrasts with data parallelism, where the same calculation is performed on the same or different sets of data. Task parallelism involves the decomposition of a task into subtasks and then allocating each subtask to a processor for execution. The processors would then execute these subtasks simultaneously and often cooperatively. Task parallelism does not usually scale with the size of a problem.